Howdy, welcome to Lab 13, Solutions, Electrolytes, and Concentration. I think I'll do this one in two parts, parts A and B right now, and then set up with the numbers on the second part. So in the first part, what we're doing is looking at a couple of materials and whether they dissolve in water or cyclohexane. So the issue is that water is a polar solvent, and we'd expect that polar molecules or ionic compounds would dissolve in water. Cyclohexane, we're going to use Coleman fuel rather than cyclohexane, but same thing, is nonpolar. So ionic compounds won't dissolve in cyclohexane. Nonpolar compounds should, but there's some other little things going on. So the four things we have to look at here, we have an ionic compound, we have iodine, which is a covalent compound in this case, not iodide, but iodine, sucrose, which is table sugar, and vegetable oil, which is just the oil we might cook with. The only ionic compound I could find around the house is copper sulfate. And the nice thing about either copper sulfate or potassium permanganate is that they're both very colorful, so they're easy to see if they've dissolved in water or not. So without further ado, here's a sample of copper sulfate. It's kind of a colorful blue, slow to dissolve but soluble ionic compound. And here are a sample of, I already did the water, so I have water here that we can see some has dissolved, some of the copper sulfate is dissolved. And if I do the same thing, that is if I put the copper sulfate in the cyclohexane, and you gotta trust me on this, but if I let it sit here for quite a while, we would not see the copper sulfate dissolve. So again, very clear that the blue solution results from the solid copper sulfate going into solution and forming aqueous copper sulfate. So what we're supposed to do then is here we say that it is soluble in water but not soluble in cyclohexane. All right, iodine, somewhere in my backpacking water purification kits I have some, but I can't find it. But what will happen is it does not dissolve in the water, and it does dissolve quite readily in the cyclohexane. All right, sucrose. We've got a little sugar in a raw here. So if I take some of that and put some in water, and what I want to see is as this slides down through the water, if I can see that well enough, I might see what's called Schlering lines. Yeah, it's hard to see. So we put a little bit in, we'll give it a shake. We'll put a little in the cyclohexane. Oops, I got a little water on there too, that's not going to work. I put the sugar in the cyclohexane. And when I shake these up, I find that, well, it hasn't all dissolved. I put about the same amount in each. To be consistent, the water, most of the sucrose dissolved, all of it will eventually. Cyclohexane is untouched. And again, a good way to see this is if I could really zoom in on it, you can see the kind of mirage lines as the index refraction changes when the sugar dissolves. All right, so not sure that was 100% clear, but between common sense and taking my word for it, sucrose is soluble in water, not soluble in cyclohexane. And then our last combination here, we've got vegetable oil. Right to the kitchen and got some sesame seed oil. That should work. I'll put it over here so I don't make a mess. And the water is this guy. The cyclohexane is the one on our right. And I'll shake them up real quick. You can see that the oil largely went to the bottom of the cyclohexane but stayed at the top of the water, and that's because the oil is less dense than water but more dense than cyclohexane. So let's give these guys a shake. And then what we see is that the oil dissolved in the cyclohexane. It's no longer at the bottom, but the oil is separated out from the water in the water solution. So bottom line with this one, and again, makes some sense to us. Vegetable oil is not soluble in water, but is soluble in cyclohexane. All right, where we go with this is recognizing that our polar water and our non-polar cyclohexane tell us something about whether the solute is polar or non-polar. So copper sulfate is ionic, more than calling it polar, but we'll call that polar. Iodine is non-polar, even though we didn't see that one. Sucrose is going to be polar. And the reason for that is sucrose looks a lot like alcohol if you looked at the molecular structure. There's a lot of OH bonds hanging off of it that provide the polarity. And vegetable oil is nonpolar. All right, you got a question down here about sodium chloride being soluble in water, but iodine is not. And the endings of those names, chloride versus iodine, is important. All right, the second part of the lab is a demo that the instructor usually does. I don't have it set up to do here. Ever so mildly dangerous, but what we do in this one is we have a test tube, or a beaker rather, it's in the description at the start of the lab, and we have two wires that hang down into it, and that's coming off of a power supply, and then we have a light bulb. The drawing in the book is a lot better than mine. And so what we see is that if we close the circuit by having a conductor across the two electrodes, the light bulb should light up. If the electrodes are open to the air or a non-conducting material, then it doesn't light up. So what we see going down this list is solid sodium chloride. We don't see anything, so no light. I'll just put N for no light. D for dim, and B for bright. All right, and the fact that there's no light means that we just have ion molecules or both. We don't have either, kind of not a fair question. We have an ionic lattice. We don't really have molecules. We have cations and anions stuck together, and the point here is that those ions don't have the luxury of moving around, so they don't conduct any current. If we take the sodium chloride and dissolve it in water, now we have salt water, we find out that we have a very bright light. And the reason it's bright light is we have lots and lots of ions. And so the type of electrolyte is that it's strong. Strong versus weak electrolyte means that something either completely dissociates, poorly dissociates, or doesn't dissociate at all. We'll touch on that again at the bottom. So if something separates into ions, it's a strong electrolyte. If those ions want to stay together, it's either a weak or a non-electrolyte, depending on if it happens at all. All right, sucrose, there is no light here, and so we have molecules, and we have a non-electrolyte. 1 molar hydrochloric acid, that's a very bright light. The type of particles is going to be ions. And the type of electrolyte is that it'll be strong. Acetic acid is a dim light, oddly enough. It's a D, dim. And what this means is we have both. And important here is that the concentration for the HCl and for the acetic acid are both 1 molar. So the concentration of acid in each of these solutions is exactly the same, but HCl was bright, acetic acid is dim, telling us that we don't have nearly as many ions here. We have the same number of components there of HCl versus acetate. So here at the end, we'd call that a weak electrolyte. Again, this right here, the fact that it's dim, tells me that not all of the ions have separated from each other. All right, sodium hydroxide, I can't write, bright. So we have ions here, and it's a strong electrolyte. Ammonium hydroxide is dim, so we have both, and that's a weak electrolyte. The ammonium hydroxide can form NH4 It's our ammonium and our hydroxide. Or it can stay together as this NH4OH, which can also be thought of as NH3 and H2O. All right, so we can have the proton from the water stick to the ammonium and form an ion, or we can have the ammonium hydroxide or ammonia just stay associated together. Ethanol, no light at all. And important here, you've got a hydroxide looking thing, it's OH, but in this case it's a hydroxyl because the alcohols are covalent or molecular compounds, not ionic compounds. Type of particles, we have molecules, and it's a non-electrolyte. Glucose, exactly the same thing. Other, in class we usually do Gatorade, maybe coffee, tap water. Here we'll do tap. And tap water for us is a reasonably bright. It's not as bright as the real bright ones, but we have a lot of stuff in our Glendora tap water. Type of electrolyte, you got a whole mix of things in there, but the strong swamps everything else. All right, what we want to do then is kind of understand that in terms of chemical reactions. So if we have a strong electrolyte, our code is that we write a single headed arrow, and I show that I'm getting H plus plus OH minus, and I should show that these guys are aqueous, though that really has to be the case. HCl is a pure material, comes as a gas, so I could say, oh, I have gas HCl dissociating into the ions in water, but I think this is sufficient. If we have something that's a weak electrolyte, we show a two-headed arrow, either one line with an arrowhead on both sides, or a lot of people like to write these two half-headed arrows, and that gives me NH4 plus OH minus, and again, both aqueous there. Glucose, if I wanted to write something here, I could write it as C6H12O6 solid, and if I dissolve that in water, I'll put a little H2O under an arrow, I get C6H12O6 aqueous. Again, what's key is that it's still a molecular compound versus the ionic compounds that dissociated. Oops, and I'm running off the page as usual. So again, my glucose, I wrote it as solid glucose dissolving in water to give me aqueous glucose, but there's no formation of ions there. All right, and then we'll leave this one to you guys, but the same kind of code. We've got this single-headed arrow, which tells us that something goes completely. We have a double-headed arrow, which means that we have some of the HX on the left side, some of it on the right side, and here they do our HX, which could have been HCl as a gas, like I mentioned above. Here we have some compound as a solid dissolving. Note that there's no ions, and here we have some solid dissolving to give us ions. Okay, let's ignore report sheet part C, and we'll pause and start again in part D.